Hey Con, are you sure this is a good idea?
Yeah, of course. Why?
I don't know. It just seems a tad risky to get a few extra credit points from Mr. Brower. Are you sure there's no other way to show projectile motion?
Look, it's completely safe. Trust me.
Well, could you at least take a few steps back?
Fine.
This honestly doesn't seem much safer.
Look, I swear it's completely safe. I did all the math.
You and I are 25 feet apart. The apple is 6.3 feet above the ground, while the arrow is 5.8 feet above the ground. The arrow is being fired at 23 degrees. We can set up it with that equation as distance equals half of acceleration due to gravity multiplied by time squared plus initial velocity in the y direction multiplied by time plus our original height. Because our time equals our distance over our initial velocity in the x direction, and the initial velocity in the x direction equals the cosine of 23 degrees times the initial velocity, we can say that time equals 25 feet over the cosine of 23 degrees times initial velocity. This allows us to set up the equation. 6.3 equals negative 16.08 times 25 over the cosine of 23 degrees times initial velocity squared plus the sine of 23 degrees times the initial velocity times 25 over the cosine of 23 degrees times initial velocity plus 5.8. After multiplying, dividing, canceling out, simplifying, and other stupid math shit, we find that our initial velocity is 34.2 feet per second. That means that as long as I fire the arrow at a velocity of 34.2 feet per second, the arrow will hit the apple right off your delicate little head. It's that simple.
You didn't account for wind resistance.
Negligible.
Wait, seriously, I don't think I can do this.
Come on, I really need this extra credit in physics. I have a D in that class right now.
How?
I failed the projectile motion quiz.
Fine, let's get it over with.
The second law is all about a simple formulation. To get the force, just multiply mass and acceleration. If that's too much to say, there is an easy way. Try this abbreviation for this simple formulation.
F equals M-A, F equals M-A, F equals M-A. Now that's the abbreviation. F equals M-A, F equals M-A, F equals M-A.
Force equals mass times acceleration. Force equals mass times acceleration. Acceleration. Force equals mass times acceleration. Acceleration. F equals M-A. F equals M-A. F equals M-A. F equals M-A.
Welcome to Engineering Mechanics Dynamics. In this lesson in curvilinear motion, tangential and normal component. And so to start it off, we'll draw a path of a particle. And so here's our particle. And here's our center of curvature, O. And the key to tangential and normal components is a coordinate system that has its origin on the curve. And so here's our coordinate system. And we have n, which is our normal, and our t, which is tangential. So then we have our unit vector, u sub n, in the normal direction, and our unit vector u sub t in the tangential direction. And so u sub t is the unit vector tangent to the path of the particle, and u sub n is the unit vector normal to the path of the particle. And lastly, if you split up this path into little segments, each segment could be formed from the arc of an associated circle. And so each segment has its own arc to it, and therefore its own center of curvature. So this segment has its own center of curvature, and to the center of curvature we have the radius of curvature rho. And so maybe right here we have a center of curvature for this rho. And so essentially it's the rho is the radius at that particular spot in time.
Mass versus weight, two measures for an object. They're not the same, let's all see why. To determine the mass, we use a balance to do it. We use a scale to measure weight. Measured in grams or in kilograms. It's all about how much stuff the object has. Grams or kilograms, they're the units we use for mass. Newtons are for weight. Weight's the measure of gravity's pull on the object. So you can see, mass and weight aren't the same thing. Weight is the measure of gravity's pull. In contrast to weight, mass tells us how much matter the object has. Mass, measured in grams or in kilograms. It's all about how much stuff the object has. Grams or kilograms, they're the units we use for mass. Newtons are for weight. Weight's the measure of gravity's pull on the object. Mass and weight, they're not the same. Mass and weight, they're not the same. Mass and weight, they are not the same. Grams or kilograms, they're the units we use for mass. Newtons are for weight. Weight's the measure of gravity's pull on the object, yeah.
Hi, I'm Matt Parker. I've seen a lot of confusion over the concepts of accuracy and precision. Even though people may use them interchangeably, accuracy and precision have very precise mathematical meanings. For example, in response to the question, "Where's Wally?" you could say, "He's in the picture." Now, that would be a very, very accurate response, but it's not very precise now, is it? If you said, however, he's just behind and slightly to the right of that woman getting her clothes vacuumed off, children's books, that would be a very precise answer, but unfortunately not accurate. He's over here. To remember the difference between accuracy and precision from a data point of view, just pretend you're playing that classic game, pin the mitten on the kitten. If you were to place lots of mittens all around the kitten so that none of them are actually where they should be, but yet they average out statistically to be on the kitten's paw, this would be an accurate but not precise collection of data. If, however, you were to have lots of mittens very close together with a low standard deviation as such, this would be a precise set of data, but unfortunately not accurate. So there you are. That's the difference between precision and accuracy, so please make sure that from now on you use those words use them correctly.
Now, a lot of people get acceleration and velocity and speed mixed up in their head, but I'm going to try to give you guys a really easy example of how they're different. Say you were driving your car, and you put your car on cruise control at 45 miles per hour. Now, your car would be going a constant speed of 45 miles per hour and not be changing speeds. Therefore, since you aren't changing speeds, you are not accelerating. Acceleration is basically changing speeds. Okay, so when would you accelerate? Well, let's say you were at a red light and then that red light turned green. Well, you would then go from 0 to 30 miles per hour as you would accelerate. So therefore, since your speed would be changing, your car would be accelerating.